was the last slide. I think we stopped here. Am I right? Or not? I think we stopped here, if I remember correctly. The problem here is now we are talking about torsion. What does it mean to have torsion in a beam? Shear is clear. I told you it's cutting like a scissor. You take two parts of the beam and you just slide them across. Plain, pure sliding. Torsion is twisting the cross section. So twisting basically means that you have a cross section and you try to rotate it like that. Basically it is the same as if you apply two loads on a section, one going up, one going down, causing it to twist. So that means the torsion can be decoupled or can be thought about two forces acting on the section, one going up, one going down, causing the torsion moment, correct? And then it means that if I suppose to cut the beam in half in the middle, one section will have shear going down, one section will have shear going up, force going up. So if I was to cut this beam along this middle and convert it into two beams side by side, right? And that means one side is going down, one side is going up. And that means the shear stress direction in one side will be downwards, another side will be upwards. And to balance that, there will also be, so this couple could be like this, or a couple could be like this. Who says it has to be applied like this? It could also be like this, top and bottom, same effect, correct? So that means the beam shear problem can be considered as a couple either acting up and down or acting this way. So there will not only be shear here and here, there will also be shear here and here. So torsion produces shear stresses all around the section in a loop, right? Which makes for an interesting thing here. So this creates a stress field. Look at the arrowheads. They are going like this around the section, right? Stress flow. So shear stress flow is created on the section, and this one becomes horizontal, this one becomes horizontal, this one becomes vertical, and in between there's angle depending on the size. Now the issue is this. When you have shear on the entire cross section, all of these arrows will be upwards, correct? Now half of these arrows are upward, half of these arrows are downward, and there are also arrows here, which means the reinforcement for torsion should be provided not only here but also here. So torsion reinforcement must flow in all cross section, whereas shear reinforcement only vertical is enough. You do not need horizontal part of the stirrups, right? Now, story. How many people have gone to Pattaya through Banda Road? No one. There is a bridge going from Bangkok towards Pattaya. You know where's Pattaya? Going to Pattaya from Bangkok, there are many ways to go. One way is from this side, from AIT. We used to go a long time ago. It used to take 4 or 5 hours. Then they started building this bridge. This bridge is 55 kilometers long, elevated bridge, 6 lanes, standing on a single column, goes down, and there are pile cap below that, which are 12 meter by 5 meter by 2.5 meter, one pile cap. Imagine this room is 2.5 meters, so it's as thick as this room, 5 meter wide, which is the width of this room, and 12 meter long, which is going all the way to Professor Bubble's room, right? That is one pile, and there are 1,000 pile caps like this on this project. Now what happened was, during the design, before the design was done, it was a project by a company from Germany who will invest and build. So they means their money, not government money. So they estimated and they say, okay, the pile cap before the design will be designed, and then they estimated the reinforcement like this one, not they thought torsion will not be a problem with high cap. So torsion was not considered, so they just put vertical stirrup bars, calculated the quantity, and it came out to be 75 kilograms per cubic meter. So you imagine about the quantity, right? For millions of pounds, kilograms of reinforcement they calculated. When they do the actual design, it came out to be 125 kilogram per cubic meter, which means a lot of money extra, which they don't have because they already got the project. Now they got worried, what is the problem? Why is it costing so much? So the project came to us a long time ago before they started the construction. And this is in fact one of the first projects we did on this thing, trying to figure out why it is costing so much. And you know what we found, interestingly, that pipe cap had a torsion, and they were putting the combined shear and torsion reinforcement to go around. So the cost was so high because most of the reinforcement was coming from torsion, not from, but most of the reinforcement was coming from shear, very small from torsion, because torsion was not that big. But when they combined the reinforcement for shear and torsion, they put it along this section. We just asked them to separate the shear and torsion reinforcement, put the shear reinforcement only vertical, and horizontal should only be torsion, which is very small. And that already saved them enough money to reduce the cost a lot, because this is very long, 5 meter. And if you save the reinforcement 5 meter here, 5 meter here, 10 meter long reinforcement, every 100, 200 millimeter for 12 meter long, you can imagine it's a lot of reinforcement multiplied by 1,000 of these. So it went up to thousands of, hundreds of thousands of tons of steel was saved only because we are able to separate the clearly torsion and shear behavior and corresponding reinforcement. So a small change in detail can mean millions. So the understanding that torsion and shear are two different things and their stresses are not the same, and one place we have this, you can see from here, so only put vertical bars for shear and only put horizontal bars for torsion, then we can do more optimized design. And that is what the code says. They say you calculate the reinforcement for shear separately, you calculate the reinforcement for torsion separately, you add them together in these locations, and the closed loop should only be for torsion. Doesn't have to be for shear. Correct? So this is another idea. That means if the most of the concrete is in tension because of the bending, right? And tension is already cracked, that means it is not available for shear anymore. Not available for torsion anymore. Because concrete has a tension capacity, correct? And we are utilizing that tension capacity to calculate the concrete capacity in shear. Agreed? But if the concrete beam is already cracked by bending, then that concrete tension capacity is no longer available because it's already cracked by bending. In a normal beam, at the end where we have maximum shear, we have no bending, so we have no problem. Correct? But when it is a continuous beam, you have a lot of negative bending and a lot of shear coming at the same location. So in those locations, and also for earthquake loading, which can have varying moment directions, we normally do not consider the contribution for concrete in shear. And so we can basically neglect all of that, and only a small portion is left, which is in compression. So it is advisable to design for torsion primarily by reinforcement, because the torsion is a stress around the edges of the section, and we can just put the reinforcement there and we should be fine. Tension is ignored, that capacity becomes 0. And there are 5, 6 equations for calculating VC. BC is the shear capacity of concrete alone. That normally is a small quantity. However, there is a second limit. So normally if that is exceeded, we can calculate the reinforcement for the remaining part. But then they also put this very interesting limit. They are saying, the code is saying that you cannot put too much reinforcement for shear. Unlike if you have a beam in which the compression capacity of concrete is exhausted, you can put compression steel, doubly reinforced beam, and there is no limit how much you can put. If you put the compression steel equal to tension steel, you can go to infinity theoretically. Last time I showed you the equation that you can continue to add compression steel and equal tension in compression steel, and there is no limit because the two can make a couple and carry the moment. But in shear, that is not the case. They are saying that even if you remove this one, after that the maximum shear that the beam can take, even with reinforcement, has a limit. Why? Any ideas? Why there is a limit on maximum steel that you can put for shear, unlike for bending, where there is no limit?
Because brittle failure. Brittle failure may cause brittle failure.
No, because of all the other failures that are possible. Aggregate interlock may be lost because even if the concrete is gone in tension, if you put a lot of shear in that, there is also compression failure that can come in concrete, right? There is aggregate interlock that can happen, which the rebars will not be able to sustain. So basically, the beam can be completely disintegrated so much that reinforcement is not even locked anywhere. There is no concrete left to lock the bars, right? Everything is broken so badly that there is nothing left to hold the rebars together to take the shear. So to prevent that kind of shear, which will crush the concrete and lose all other mechanisms of shear, they do not want you to go beyond this limit. And this is a serious problem engineers are facing right now, because when you reach this limit, what do? You have to increase the beam width, or you have to increase the beam size, or do something else. And many times that is not possible, especially during earthquake loading, right? For that normally governs a shear. So you end up with a situation where there is nothing you can do because you cannot make the beam deeper or wider anymore, and the shear is very large, right? Then what do? Resign and go home? There is a trick we can do to control that also. Okay? We will talk about when we talk about capacity-based design. Okay? There is a way to handle this. Many engineers are not familiar with that trick. So they will say, oh, this beam is failing, I cannot do anything, I'm sorry. Not acceptable. Right? You have to find a solution. So there's always a solution. So there is a solution to this problem to remain within that limit, and we will talk about that after when we talk about the capacity-based design. Right? So remind me to come back to this equation and tell you how we can live with this equation. In fact, a lot of research now be saying that this equation is not justified. We need to increase this limit. Some people are saying it should be 10 here or 12 here, not 8. Right? But ACI is being careful, not allowing this to change yet. Okay, more about that later. And then there is also a minimum reinforcement here that you must provide for shear. So these are code-based limits, right? To make sure that some capacity is always available for shear. So to conclude, let's summarize the shear design now before we go to torsion. You have shear. First limit is that the shear force is less than half of the concrete capacity in shear. That means shear is too small. You don't need any reinforcement. That's fine. You are quite far from the concrete capacity limit. So let's say concrete capacity limit is 10, and your shear is 4. Okay, nothing to do, no need to do anything, no reinforcement. However, if the concrete capacity in shear is 10 and your shear is 8, you are still less than concrete capacity, but code will ask you to put some minimum reinforcement here, just in case. Right? Just in case the concrete cracks, you still have some reinforcement. If your shear is more than 10, let's say it's 13, then you have to provide reinforcement for 3. 10 will be taken by concrete, 3 will be provided by steel. And suppose the maximum concrete capacity to carry shear is 20. You are between 10 and 20. You can calculate the difference between your shear minus 10 and the remaining goes to BS steel. If you are more than 20, stop. Right? So basically we have these 4 zones of shear design. Clear? Okay. So this is just to give you more idea. There are also then limits on rebar spacing. Why there is a limit on rebar spacing? Come on people, think. Don't you remember we started with the angle, 45-degree angle? So if the crack is like this one, at least one bar must cross that crack zone, correct? Otherwise, your bar is not going to work, correct? So if the beam depth is, let's say 500, your spacing cannot be more than 500, 45, otherwise you will miss one crack, and then that crack will cause the failure, correct? So the spacing automatically, one limit is governed by the depth of the beam. So the spacing should not be more than that in any case, right? And then some other cases they put D by 2, D by 4, but basically all they are trying to do is at least 1 or 2 bars must cross the crack line, which is 45 degrees typically. But the angle can change depending upon the moment and other forces, right? Okay, go back and see that figure again where you have the principle. So it's all related to Mohr circle. When they were teaching you strength of material and they taught you Mohr circle, you must be thinking, why do I need to learn Mohr circle? Now you know why Mohr circle is so important, because it relates to the shear and flexure problem and angle of the stirrups. So it is all connected. And then also this one, so D by 4. So there are many limits. If the shear is too high, then you reduce the spacing. If the shear is small, increase the spacing. And in seismic zones, you decrease it further, limit it to 4 inches because of the confinement. So everything has a reason behind it. And at this level, you must understand why these limits are there, not just believe them because they're there. You must be able to question them and understand them. Why D? Why D by 2? Why D by 4? Why 4 inches? Right? Everything has a reason behind it, and you must understand why a certain limit has been put there. Correct? This is another issue, ductile frames. Now we are talking about earthquake. What is ductile frame? What is ductility? Okay, we will talk more about ductility, but basically, just remember the ductile frame is a frame which can sway, can move, flexible, and it will not crack, it will not fail, but it will move a lot, right? So if it is going to move a lot, or will be able to deform a lot without cracking, we need to make sure that the shear is not going to cause it to fail first, right? So there are special provisions for beams or frames which are supposed to be ductile, especially for earthquake, high earthquake zones. Normally we classify the frames into 4 categories. What are those 4 categories? Anyone? OMFR, ordinary moment resisting frame. That means this is ordinary. no special provisions. It is basically not taking any earthquake or any large winds or anything, just normal gravity load, right? Intermediate moment resisting frame, special moment resisting frame, and special ductile, something like that, 3 or 4 categories. So basically, each level of frame has a more capacity to absorb the lateral loads without damage, and it depends upon which zone you are living in. What is the earthquake zone? If you are in Bangkok, maybe OMRF or IMRF may be okay. If you are living in Manila or Nepal, for example, you need SMRF, special moment resisting frames. Okay? So then the rules change, detailing and many things. We will talk more about this one, but I'm just telling you that when you talk about that, one of the key control in the ductile frame is shear. We want to make sure that while the frame is able to absorb large deformations, shear will not fail first. Because if it fails in shear, everything is gone, nothing left to. So shear and torsion have a very special place in that one, and there are many rules about that. I don't want to go into too much detail, just warn you right now. Mr. Ong will come and he will give you more details exactly what needs to be done, okay, after the midterm. This is just more details on how the concrete shear capacity and flexure capacity and shear failure, they interact with each other. Again, most of it coming from the Mohr circle and also compression field theory and other theories. So they're trying to tell you this is a very important parameter, A over D. A means shear span or length, where the shear is active, and D is the depth, and that controls the shear behavior because that controls the B and D region. When A over D is in this region, 1 or 1.5, this region is called disturbed region. Normally we have no problem with it. The shear disappears. When we have A over D equal to 1 or 2, shear problem disappears and it becomes a compression problem. We will see that. Okay? Shear becomes more in this region. Primarily, it's inclined, just very straight, pure bending, and this is a very complicated region where we have interaction between flexure and shear, quite heavy, right? Moment and shear, because of the angle of the principal stresses, is not 45 or horizontal, right? So these are just to indicate to you that okay, shear and this have interaction that needs to be considered, and we will come back to this zone again when the shear is in this area. This is the normal zone that we are talking about now, where we can use the equations that the ACI is given you, right? And for those areas which fall here, this is I already showed you this diagram. The shear problem actually in this zone is no shear, so there cannot be a crack here because the force is transferred directly in compression. In between there is a shear problem, and here in this zone we have different kind of issues. Cracks are a different way, so shear is beyond this direction is not shear. This is the area where the shear span is very small. This portion here. So this is showing you various ways where the shear failure can occur in deep members and shallow members. So it's not just only the tension in concrete which causes shear failure. There could be many other reasons, crushing near the load, and also this horizontal cracks and type of failure, anchorage failure, bearing failure, flexural failure, failure of the compression struts, and so on. So this slide about the deep beams, we have a complete detailed course on that. Okay, So shear, beam shear, when as long as the beam is in Bernoulli's range, we have very clear formula, the codes are very clear, procedure is given, everything is primarily designed based on the Moore circle concept, right? As soon as we go into the D region, disturbed region, all of that theory will not work, we need different arrangement, which as I said, we will talk about later. So for this, until midterm, we only talk about normal beam theory. Now within that, now we come to the torsion. When we want to combine torsion and shear, what do? We already decided that now we treat them independently first and simply add. This is so much simpler than what we used to learn, in which you need to calculate the available tension capacity of shear and torsion combined, because both of them are trying to eat into the same tension capacity of concrete. One side positive, one side negative. So the equations are really complicated, as you can imagine, right? So now it's torsion we can separate into independent problems. Before we go to torsion, I would like to mention that torsion has two types. Maybe I mentioned before also a little bit. Compatibility torsion and stability torsion. Okay? And there are two views of the engineers about this torsion. One group of engineers believe, or they are too lazy, so they say, I don't need to worry about compatibility torsion. I will not design for compatibility torsion. Let the beam fail in compatibility torsion. I will tell you what is compatibility torsion. Second torsion is stability torsion. There is no escape from stability torsion. We must design for that. Now, what is compatibility torsion and what is stability torsion? Anyone knows about this? What does it mean, compatibility? What does it mean, the word compatibility? Nobody goes to the dating services, they have compatibility index, right, between the two. Before people get, they say how well you are matched together. Compatibility means matched together, right? So compatibility means that we have to see whether the shear is coming, the torsion is coming because two members are trying to be matched or compatible with each other, or it is a problem in which one member is alone and it is going to fail if there is no shear. So if two people are together, then if the torsion is failing, another member of that compatibility couple will take the force. So the failure will be prevented. So two members work together to carry the load in such a way that even if one member fails in torsion, the other member has another behavior which it can carry. Correct? So to make it more clear, maybe I have a slide. So let's talk about that later. Now first of all, let's see what is the way to design for torsion, whether compatibility or stability torsion. Suppose if we must design for torsion, what is the way? The way is that we calculate certain properties of the cross section which are shown on this section. If you remember, the first slides that I showed you torsion stress flowing around the section, correct? In the middle, I told you there is no torsion stress. It's only on the edges, as far from the section as possible. Based on the same concept, they are saying that this portion of the beam has no contribution to torsion, zero. Because it's inside the section, no stress there. All the stress in torsion is at the edges of the section. How wide? They define that region to be a certain, let's say, stirrup. So this is the stirrup. So all the concrete or all the portion in this area plus the stirrups, these are the only one that we are going to talk about for torsion. The rest is not our concern. Just like when you do the bending, all the concrete below the neutral axis is neglected. Correct? Same way, all of the concrete in between this one is simply neglected. So now we are left with a simple tube of the concrete and steel section around the section. And these properties ACP, ACO, AOH, PCP, PN, they simply are measures of that area. Length of that area of that area, something like that. Correct? So these are very easy to calculate, these properties. You can see from here. For rectangular beam, ACP is equal to BH, AC, AOH is equal to that one. Very, very easy. Correct? This was not the case earlier. Earlier we need to calculate the J, we need to calculate C1, C2, TJ, many complicated formulas that long to calculate torsion. That's why many engineers choose not to design for torsion at that time. Now it's easier. So you calculate these few factors. Based on that, you can calculate the capacity of the beam in torsion. And same way, exactly the same way as in shear, if the torsion is very small, you can neglect it. That means you do not need to provide any reinforcement. If torsion is more than the concrete capacity, based on that outside piece of concrete, then you provide reinforcement for that. Then you calculate the shear reinforcement, you calculate the torsion reinforcement, you put them together. Vertical are added, horizontals are not added. Remember that. But in small beam, it doesn't matter. So we just provide the same all over. But in bigger beams, you can separate them, as I showed you the example. Are you following me or not? Okay. I don't know if you said yes or no, but I just said okay. Either way. So based on that, for non-prestressed members, based on this one, we can calculate the concrete capacity for torsion. Remember this diagram, this number again? Tension. Exactly. So torsion capacity of concrete is also equal to related to the tension capacity of concrete. And this is the property of that circle around that. Correct? So very simple. And then for this one, you can calculate for pre-stressed members. Okay, we have this one, forget about that. For non-pre-stressed members, subject to an axial tension, we also can add tension and compression into that, because torsion and tension are, they act together, because torsion gives axial stresses also. Shortens or elongates at the same time, right? I told you the problem of the torch steel, that you can twist it and the axial stress strains. So axial strains and axial stresses are related to torsion and shear both. So torsion is a link between bending and shear. Because shear is vertical, bending is horizontal, torsion has both. Longitudinal and shear. Up and down, left and right. So torsion is very, very terrible thing for anything, right? Because it has everything which you don't want. But anyway, these equations help us to simplify that. So after we calculate the concrete capacity in torsion by using these equations, then if let's say the torsion capacity of concrete comes out to be 10. What would be the units of torsion? This by the way. What is the units of torsion? Sorry? Okay, Newton millimeter, whatever, but it's a moment, right? It's not shear. So that automatically tells us that it is something to do with the moment. It's a couple, right? Two forces together. So if the torsion is, let's say, the capacity of the beam in torsion is, let's say, 1 ton meter, and your torsion is 0.4 ton meter, nothing to do. If it is more than 0.5 ton meter, minimum reinforcement. More than 1 meter, all of the torsion must be taken by steel. And similarly, so we have the same limits. Query, side by side like shear. And finally, you calculate the reinforcement for torsion, from shear, put them together. And spacing limits for torsion and shear are a little bit different. So if you have torsion and shear both, then the higher of the two will apply. Let's say torsion wants it to be d by 2, shear wants it to be d, you use d by 2. Correct? Because the limits for shear and torsion reinforcement spacing are not the same. Torsion requires more closer reinforcement. So that is the what I was telling you about minimum longitudinal T-bars area. Now this is interesting. When you design for torsion, you not only design these stirrups, you also add horizontal bars along the beam length, because torsion, as I mentioned to you, has both components. It produces shear and it also produces tension. So to take care of the tension, AL, longitudinal bars, must also be calculated and added to the top and bottom bars of the beam along every place. So when you have torsion, you calculate the vertical components and horizontal components and add them as shear reinforcement, and you calculate the longitudinal component and add them to the longitudinal bars. So it's really complicated because you need to add the reinforcement in many places. And that is why people do not like torsion. So they also, now when it comes to maximum torsion capacity and shear, then they are combined together. It's okay, the maximum torsion and shear together must not exceed that limit, because shear has already been set. Maximum shear capacity is already been set. So the total shear from torsion and shear must not exceed that. This is the only place that these two are combined together. So that the maximum is still checked from both of them together, not independently. The reinforcement is independently, but the total limit is checked by the combined effect. Okay, think about this cantilever beam, right? When you put load on this, what will happen? It will twist this beam, correct? And if this beam, so torsion will come to this beam. If this beam fails in torsion, this thing will fall down. The only thing holding this in place is the torsion capacity of that beam, correct? Same is the case here. If you have this beam like this, if you apply the load here, it will produce torsion in this beam. If this beam fails in torsion, this will fall down. This load will fall down, correct? Same thing here. If this is a beam, there is a beam here, this is eccentric, this is going to produce torsion here, right? If it fails, this thing will fall down. These are all called stability torsions. That means if the shear fails, things will fall down, correct? What do you think is a compatibility torsion? When will the thing not fall down if it fails in torsion? This case. Suppose you have a beam here, right? You also have a beam here, and you have a load here. So when you apply the load here, this will bend here, and also it will have, because it is connected, it will also have torsion, negative moment here, torsion in this beam, and torsion in this one. Correct or not? But if this beam fails in torsion, what will happen? Nothing. In a sense, yeah, good. Why? Why not? Because this means that if this fails in torsion, this negative moment will disappear, this moment will become positive, a little bit more, but it will not fail. I think I need to draw because this diagram is not very clear. How much time? Because I can maybe... Yeah, okay. I don't want to shut this down. Okay, let me finish this lecture and then come back to this diagram. 2 more very important slides and we come back to this. I'll show you why nothing will happen. Okay, let me complete this, then we go back to that one. The important thing now is that we have discussed 6 actions. What are the 6 actions that we are talking about? Come on. No, start with the simple ones. Axial tension, right? Shear, vertical, shear horizontal, moment 1, moment 2, and torsion. Correct? 6 of them. And in any structure which is a general structure, all 6 will be present. When you do the analysis of any normal structure, you will find that you will always have these 6 present. Even in a beam which is supposed to only have, how many should be in a beam? 2. Normally, beam should have only 2. Shear, vertical, and bending moment. Correct? Column should have how many?
Shear and bending.
Correct. Should have 3. Beam should have only 2. But in reality, column will have at least all 5 of them or 6 of them. Right? Beam will have at least 3 or 4 of them. Right? And if it's an inclined beam or a staircase or something like that, it will have all 6 of them. So the problem then comes that if we have all 6 of the actions coming at the same time, how do we design and put the reinforcement together? And how do we do this all in one go? And one of the way to do that, to handle them all together, is going to be space stress analogy, right? Which I'm not going to discuss now because that is next topic. But before we go to space stress analogy, let's put together the reinforcement that we need from our normal theories. Let's say we have a beam which is a T-section beam, and we have only axial load P, right? Where should the reinforcement go for load? Suppose the load exceeds the concrete capacity in compression, or the load is in tension, in which case concrete has no tension capacity. Where should we provide the reinforcement?
Bottom and top.
No, it's a column. It should be distributed everywhere. Not bottom. There is no bottom. There is no top. This column is standing like this. So the reinforcement should go vertically and distributed in all the sections like this one. So you can have the bars placed everywhere because the compression stress is constant, tension is constant. So reinforcement should be distributed evenly every place. Correct? So if it's only one action, which is compression or tension, we provide the reinforcement distributed on the sections everywhere. We all agree? So if you are very lucky and you have a case in which you have only tension or compression, which is possible, you provide the reinforcement uniformly distributed on the cross section. Done? Suppose now the same section so total AS is calculated and distributed everywhere. Moment about X, where should the reinforcement be? X is the horizontal axis here, right? So where should the reinforcement be?
Top and bottom.
Top or bottom? Top or bottom, and top and bottom. What is the difference between top or bottom and top and bottom?
The section is sufficient to resist the stresses we provide. The bottom section is not
Depend on, first of all, top or bottom means moment direction. If the moment is positive or negative, depending on that, reinforcement will either go to top or bottom. If the moment is too large, then both top and bottom, right? So make sure that you understand top or bottom means moment is small but the direction is negative or positive. Top and bottom means the moment is large, so you need tension and compression, both. So it will go to top and bottom depending upon where the direction of the moment is. So moment direction is very, very critical. For a beam, normally we always think it to be positive or negative. But in earthquake, it could be positive or negative at the same location because the direction is changing. Okay? So based on that, we need to calculate the reinforcement and provide at the top or bottom and top and bottom. And sometimes we also need reinforcement in the middle. Why? For bending. You're shaking your hands like this, but I'm asking why? No, no torsion. I'm just saying for pure bending moment, only bending moment, we also may need the reinforcement in the middle. Why? Normally called ASW. So we have AST, ASC, let's say moment is positive, tension at the bottom, compression at the top, and ASW in the middle. Why do we need ASW? Because if the beam is very deep and you have bending moment, most of the beam will be in tension because the neutral axis depth is very small in beams. So it means that if you only provide reinforcement here, the middle portion of the beam will crack. Because you have the whole beam and it is all of the web is in tension, but you only provide reinforcement at the bottom. Last time I told you about cracking moment and I said spacing is very important. So that means the distribution of the reinforcement is critical. So if you provide only here, you will find that there are cracks in the beam, vertical cracks in the beam at regular interval. They don't go all the way down, but in the middle portion because there is still tension, but no reinforcement. So if the beam depth is more than 1 meter or about 36 inches, you need to provide ASW also. Clear? So for bending, we need reinforcement top, bottom, and also in the middle, depending upon the depth of the beam. Next one. MY, that should not be MX, please correct that. It should be moment MY. MY. That means if the moment is about vertical axis, right? So you need AST depending on the direction, reinforcement here and reinforcement here and also in the middle, same way, right? And in the middle. Depending, so if the moment is like this becomes tension and compression, where reinforcement comes here. If the moment is like this, primary reinforcement here and there, and the web reinforcement in the middle. Correct? So now you can imagine the moment directions this way, the moment direction this way, the same reinforcement has many meanings. Okay, shear. If the shear is vertical, you need reinforcement like this and like this. Nothing here, remember, only vertical. Right? We don't need anything else because shear is like this. So one rebar here, one rebar will be. If the shear is horizontal, you will need reinforcement here and here, not vertical, then only horizontal. So basically you need reinforcement along the direction of the shear force. Correct? And it should be anchored properly so that reinforcement can take tension. Rebars for torsion now, where should they go? Where should they go? Like that. So first of all, we should have this stirrup going all the way around here. And sometimes we may even put shear reinforcement here if the shear flow is going like that. But normally we don't do that. But sometimes we may do that. If this is big enough, we might provide stirrups like this also, which can also take the shear flow going around this one. If it is small, we don't do that. But we may do that. We have to follow the shear flow. And you also need longitudinal reinforcement going perpendicular to the surface for AL. So A, SVT and AL are calculated and provided like this. right? So you can imagine now this reinforcement and shear reinforcement must be added together. This reinforcement must be added together with the moment from bending or from axial load, from compression or tension, or bending about X or bending about Y, right? So this reinforcement can have many purposes depending upon how many actions are there. So the total reinforcement in a section could be like this, taking into account all 6 actions. So far we have been just talking about top and bottom being rebars, right? And we said, well, we have to. But actually there are 6 actions, and there are a lot of reinforcement coming from those actions, and they could all be interacting with each other. Same reinforcement serving many purposes. For example, this bar could be a tension bar for moment, could be a compression bar for axial compression, could be a tension bar for tension, could be a longitudinal bar for torsion, or could be a compression bar for another moment direction. Or if the moment direction changes, same bar could be a compression bar or could be a tension bar, right? So that means it is quite hard to really find out the amount of each rebar and what it is doing. How much of the bar is going for compression, how much the bar is going for bending, how much the bar is going for torsion, right? Same bar here, so it has many functions. Which basically means what? Basically it means is that once you calculate the reinforcement, you provide the reinforcement, you need to check to make sure that all the actions that are coming can be taken care of simultaneously if they are coming. Correct? You may calculate the reinforcement individually, put them together, but final amount must satisfy the requirement for all of them at the same time. Now, interesting thing is that if you provide a bar here, this bar maybe you design for compression, for tension. It also can take compression. So if the compression amount is larger than tension, you provide compression amount. If the tension amount is larger than compression, you provide tension amount. So we have to make sure that each of the location, the reinforcement is sufficient to take care of all of the effects from various actions that can come there. So that was the bottom line of this whole concrete cross-section design. Everything else is details. Design the column for every load combination as if it was independent, and take the highest reinforcement at each location for all the combinations and finally come up with a final amount, so that all of the load combinations will be satisfied. Correct? Let's say you have a beam, and one load combination is saying it's a positive moment, and you need tension reinforcement. One load combination is saying it's a negative moment, and you need compression reinforcement. So for compression reinforcement, you calculate compression amount. From tension, you calculate tension amount. Whichever is higher is provided there. So it covers both. Correct? So same rule goes for every action. So if I apply a load here, there will be a positive moment in this beam, correct? And there is a negative moment because the two beams are connected, and this negative moment will become torsion for that moment, that beam, correct? Because they are connected. When this beam deforms, it will twist the beam at the end, and that beam will be in torsion. Now, if this beam fails in torsion here and here, what will happen is that this torsion capacity will disappear, and then this will rotate further, and this moment diagram will become like this. No negative moment anymore at the end, because that beam cannot take torsion. Or another way, let's think of another case. that we have a beam here, and here I put a hinge, correct? If I put a hinge here, then the bending moment diagram will be like this, correct? But the beam did not fall down, it is still stable. So that is what I was saying, that even if we do not have any torsion capacity of that beam, the structure will not fail. However, if I have no support here, and I apply load here, the bending moment diagram will be something like this. I must get that torsion here, because if I don't have that torsion there, right, this beam will fall down. If in another case, I have another beam, and I put a hinge here, and a cantilever here, try to apply load here, nothing. This beam will just fall down, right? So this is a stability problem. This is a compatibility problem. That means if you ignore one action and another action is available to take care of the load, then it is a compatibility problem. In an extreme case, this is also interesting here, and we will continue with this example later. This is a beam, correct? What is that? Bending moment diagram, correct? Right. Suppose I say that, okay, and one more. I say that, okay, I have hinges here and I have hinges here. I do not have any negative moment capacity. So the bending moment diagram will be like this. But the beams are not falling down. So even if I do not design for negative moment, I do not provide any negative reinforcement, the beam will become like this. The positive moment will increase, but it will not fall down. Or I can say I have a hinge here. So in which case the bending moment diagram may be like this. One cantilever here, and it's still fine. Correct? So which means for an indeterminate structure, a structure which is indeterminate, you know what an indeterminate structure is, I can choose to make it compatible, and I can choose to introduce hinges until it becomes determinate, and until that point I can play with the reinforcement and shift the moment diagrams here and there as long as it doesn't fall down. Correct? Same is the case with the compatibility torsion. If the structure compatibility torsion is coming from indeterminacy, then it is a compatibility issue, and you can choose to reduce the torsion capacity or ignore the torsion and produce artificial hinges to neglect the torsion design. But if it is a determinate structure, it is a stability problem. You cannot neglect it. You must design it. So many engineers choose not to design for torsion in case of compatibility, or they choose to reduce the torsion to 25% or 10% of the actual value, because the real compatibility torsion is too high, and it is not correct also. Why? Tell me why this compatibility torsion that I calculate from the analysis is not correct. Because the compatibility torsion I am calculating is based on the gross cross-section properties of the beams. Gross cross-section properties of the beams are not real. Beam is going to crack. The actual cross-sectional properties of the beams will be much smaller than that. So the calculated elastic forces are incorrect anyway, because they are based on gross sections, which is not the right estimate for a reinforced concrete section. So this gives us the opportunity to actually go to a compatibility torsion design in which we can reduce the torsion to some extent. Some people reduce it by 50%, some reduce it by 25%, some reduce it by 10%, something like that. And in fact, the codes allow you to have a cracking factor onto your moment of inertia, so you can alter these values significantly. Okay, let's stop here. Any questions?